Everyone, thank you for being here, and it's a pleasure to welcome Professor Petar Momcilovic from Texas A&M, where he is associate professor in the industrial systems engineering department. Petar got his PhD in electrical engineering from Columbia University, published extensively with numerous distinctions, including the IBM Faculty Award and the NSF Career Award. And his current research focuses on modeling and analysis of large-scale stochastic systems, which is what he'll be talking about today. So please join me in welcoming the speaker.
All right, so I'll jump right in and kind of describe the problem here. So I encountered this problem from the systems biology angle. So think of this: there is a cell, and there are these molecules, I'll call them monomers, that are floating around, okay? And then they attach to structures that we'll call filaments. These are linear structures. So, here in this example, I have 6 different filaments, and these molecules are floating around and attaching themselves. And in particular, there is some rate of attachment for a given filament to a particular monomer to a particular filament here, for example, lambda, okay? So this is kind of growth. This is the growth network here, but also monomers detach from a filament, and that happens with some rate mu. Okay, so in this example, I have 6 filaments, and I try to make these circles and these squares to denote that these are different types of filaments. Okay, all the filaments are not uniform. There are different types of filaments. Okay, but this is the process that there is a constant attachment and constant detachment.
And only the outermost detach, or can they all detach?
Yes, only the outermost detaches. Yes, that's a good point. There are other models where there are different models of detachment, but in this particular model, the outmost one detaches. Yes, one at a time. Right, so this is kind of the basic model. Right, this attachment, detachment. Parameters of the models are what are the rates of attachment, what are the rates of detachment, how many filaments, and how many monomers in total. Right, but this is in principle, this is a closed system, right? Monomers don't arrive from the outside, don't leave, they remain in the cell. Okay. Any questions on how this model works in principle? Now, this is kind of how I started on this model. But later on, I learned in the last 5 years, the same model that I'll use for this has been used to model car rentals and also to model ride sharing. I'll come back to that to explain how that fits all together. Right? But it's essentially the same model. It is really, I just kind of arrived to this from a different application point of view. Now, this is kind of the model that works here, right? I have this closed system with M customers. So these customers are my monomers in the system, right? They're floating. Now I have this infinite server station, right? Which represents all the monomers that are not attached. They're floating around. Right? And then, if I look at a given monomer, let's say here, this customer, it attaches to this filament with rate lambda 1 and so on. So the total attachment rate, you can think of this is lambda. Right? That's the sum of all rates. Filaments are these Qs. Okay, these Qs. I have a bunch of them. I have F of them. Okay, so there are F filaments here in total. And the way this works, servicing this Q, right, represents that filament is losing one monomer, so monomer is detaching and it's going to what people call free pool. Okay? This is kind of the model, right? And I have this F single server queues. I'll use L1, for example, to denote how many customers I have here. This would be how long is my filament, right? How many monomers it contains. The longer the filament, the more customers kind of I have here. Okay? But this captures this idea of attachment and detachment. Okay? So long Q means long filament. Now, I also did one more thing here. I ordered these Qs according to this parameter, what I call kappa. This is the ratio of detachment rate versus attachment rate. Okay? So I order them such that at the beginning I have Qs that have the lowest kappa. Lowest kappa. So it is the lowest. So I say that there are F1 Qs with the lowest kappa. This F1 can be 1, can be F, can be everything, right? If it's F1 is F, then all of them are the same. If I have uniform filaments, if there could be only one that's has this smallest rate and the rest of them higher rates. Right? Question.
So the lambdas are independent of the L's?
The lambdas are independent of L's, right? This goes back to this picture here, right? Lambdas are kind of determined by this attachment location here. So it doesn't really matter how long this is.
Okay, so this is a filament, but otherwise I would have assumed that the structures inside the cells, the larger the structure, the more accumulation.
Yeah, there are also people looking at a model that are 2-dimensional, 3-dimensional, where things are being built. Yes, I'm looking kind of at the baseline model.
Okay.
Yes.
So each individual particle
Uh-huh.
has a attaches at rate lambda I.
Lambda I to a filament I.
Then the total rate at which they're attaching depends on how many are floating around.
No, so this lambda is specific to one monomer.
But if there's like how many monomers are in the
The-
square would determine the overall rate at which they attach to it.
Yes, I'll come to that also. Yes, right. So this this is the picture, right? So what you ask me here is there is some rate here, call it alpha, which I can compute based on these parameters. What is the sort of total rate of detachment and the total rate of attachment? That's the same rate because there is balance, right? In steady state, how many detach on average is the same as how many detach. So that's alpha that can be computed based on these parameters lambda and mu and how many Qs I have. That's something that I can, I look at traffic equations and I solve that. Okay. Any other questions so far?
So I mean, I guess the inverse of the kappa is the kind of how congested that Q is.
Right. So inverse of the kappa is how the congested the Q is, but really the utilization of the Q also depends on this alpha. So this is some kind of call it normalized how congested it is, right? So these Qs that I made in bold, they have the lowest kappa, they're the most congested Qs. They're the most congested Qs. There's
So the longest filament.
yes, they're potential bottlenecks. I'll call them out for now potential bottlenecks. They're not necessarily bottlenecks, they're potential bottlenecks. They're sort of the Qs with the highest load. Right? That's absolutely correct. Any other questions on how the model works? Okay. Now this model, 50 years old. In the 70s, people had this model. Right? But as I said, in the last 5 years, I saw people doing analysis of this model in terms of rental cars and ride sharing. So for rental cars, what they do is each customer is a car. The queues are rental locations. So if you look at the length of the queue, here is how many cars you have in the parking lot. And then service or detachment is somebody renting a car. Then they drive it around and then they return. Okay. For ride sharing, this is how many, you can think of this different parts of the city, how many free rides I have, Uber rides I have here. And then service is somebody requesting a ride, they go on a ride, and then the car becomes available, but they go to some other thing. Now, I'm looking at the model where there is only one infinite server station. This is one free pool, but the methodology they have works for arbitrary number of pools. I could say, if you detach from this queue, you go to a different pool, and from there you have different routing probabilities to these queues. And I can make this as complicated as you want. The only reason I didn't do it is complicates the picture, the essence of the talk and methodology. So I'll keep it to this. But fundamentally, this can be as complicated as you want, this side of the process. Okay. So again, this is this rental car business and rideshare, and this is last 5 years, even though again, the model is 50 years old, it kind of came back. Now, all right, so what am I talking about here, right? I'm looking at the stationary distribution, I'm looking at the state, right? And then going back to the 70s, this is a product form network. And it turns out that the stationary distribution, how many customers I have in each of the FQs, is given by this expression. Cap was the right parameters of my model. And then M is the total number of customers. And I'm only looking at the distribution such that the total number of customers in the queues is at most M. I have a closed system. It cannot be more than M. If it's more than M, the probability is 0. And of course, this thing here is the normalization constant that if you sum up this probability, you get 1, and this C normalizes everything to 1. That's people call it partition function. And as you see here, that there is no M here. M is the total number of customers I have in the pool on the infinite model, and that's because if I know how many customers I each Q, then I subtract the total number, and that will give me how many are free.
So the arrival process is deterministic?
No, the arrival process is here. It takes some exponential amount of time for this monomer to attach somewhere here.
But the L's are not averages.
The L's, these L's don't determine the rate. So think of this. The only thing that matters as far as this rate is going from here to there is whether this is busy or not. If this server is busy, right? If this server is busy, the rate out is mu1, whether you have 1 customer here or 5 customers. So it kind of, if you're looking at the average rate, this alpha, you kind of have to compute what are the chances that this is empty, and that will tell you what is the average rate of throughput through this queue. So yeah, that's why I said there is some traffic equations that one needs to solve to get this alpha, but you know it's doable. It's kind of very standard. There is nothing research about it. Okay, does that answer the question?
Yes. Thank you.
All right. So then, this is product form, and product form I can verify it here. It's called because if I look at the MM1 queues here, I have F of them, so product times the distribution of the MM infinity. This is MM1 formula, this is MM infinity Poisson distribution. Then these red things, this is the true utilization, if you want. The red things cancel, blue things are constant. You can take them out and put them here, and that's why people typically write this formula right away. They don't bother with this. But it's just to show that this is just product form, nothing else. It's kind of very simple. Okay. So now, what I'm interested in is the marginal distribution, right? I want to know how long is my filament, how long are the filaments, right? If this is happening in a cell, if I measure, how long, right? And the answer is, it's easy. I know the joint distribution, marginal, you have to sum up here everything except this L being fixed. This would be it, right? And I'm interested in the case where the number of these monomers is large, when M, the number of customers is large. Okay? And I'm going to say, well, I want to look at all cases. I want to look the number of filaments to be arbitrary, large, small, anything goes. Okay? Now, this is, 70s, but it's not as simple because, if M is large, M is, let's say M is 10,000, F is, 100, then the number of combinations you have here is enormous. This is just combinatorially, brute force, you cannot compute this constant C. You cannot compute this sum, it's just so many combinations. And this is a known problem, since the 80s, and people address it in various ways. Mostly, they deal with either transform or numerical methods. If you tell them, here's my set of kappas, here are my parameters, there is they have some kind of numerical approximation scheme to compute this with certain precision. Right? That's where the research was, right? And the research was also trying to stay away from bottlenecks, right? People not really interested in large queues. People try to avoid large queues in service systems. They try to look at a system that have small queues. But here, large queue means big filament, which is actually of interest to me. I want to measure how large. Okay, that's the main difference. But more importantly, I'd say the main difference of what we did is I'm interested in the landscape of operational regimes, right? I'm not interested in one particular solution of this. Like if you tell me, here are my kappas, here is M, here is F, tell me what's the probability that the Q is of size 10. I'm interested in all operational regimes. I'm trying to understand how this model behaves overall, in what kind of regimes it can be. Okay? Now, that's the more recent, right? This, I'd say numerical transform methods, that's a little bit later, but this is the state of the art, what's happening.
In practice, how does the sum of all the L's compare to the total number of filaments? Are we considering cases where it's possible that there's nothing in that infinite server, or do we want or is almost everything there, or is everything on the table?
It depends on the operational regime. It depends on operation. In some regimes, I can pick a regime such that almost everything is in filaments versus everything is in the infinite server pool. Yes.
So you want to look at intermediate and extreme.
I'm trying to get a big picture, right? I'm not interested in one operating regime. I'm not trying to understand the whole thing. Right. That's the main difference. All right. So now, any other questions? All right. Then, so now it's like this. I'm no good in understanding this sum. I mean, if I tell you now, hey, change a few kappas by 10%, how would the result change? I would say I have no idea. Okay. So I need some other angle how to attack this. Okay. And that's the probabilistic representation. Okay. So now, what I'm going to do, irrespective of what I have now, I'm going to define a few random variables that are independent of everything else. I'm going to define one Poisson random variable that has mean kappa 1. And I'm going to define a bunch of geometric random variables that have parameter rho, that's the ratio of these kappas. Okay. So you can think of this rho as the relative load on Qi. You can think that those most congested queues have load 1, and those below that I had in my picture, they have smaller load, and that's this rho. Okay. So what I do is if you look here, right, I have this special font for M and L's. Right? And this corresponds to the true M and L's that I have in this picture. So there is this special M now here somehow, and there is a special L here. Okay. Now, how did I come up with this needing to be defined? I said like this, well, what would happen if these potential bottlenecks are always busy? Suppose these are always occupied, they're never empty. Then the output here is just a Poisson process. I get an open system, I can solve for the rest of the system, and I would get this special L's, a special M. Right? So in a sense, if I had an infinite number of customers, the distribution for non-bottleneck queues would be this special L, not this L, that would be the same. And the number of customers here would be this special M. Then the whole system will become open system. But of course, I don't have infinite number of monomers. This is wishful thinking. This is like, oh, well, how would happen? Okay, but this is how I define this L's. So the special L's are only defined for queues below this line. So I don't have special L's for the potential bottlenecks. Okay? Now, how to connect these special variables with the problem I'm trying to solve? And here is the probabilistic representation. So this is a marginal distribution of a particular Q. I'm here writing probabilistic representation only for potential bottlenecks. I have other expressions for non-potential bottlenecks. I have also an expression for the infinite server Q. I just didn't write it here because it's kind of messy. And one thing to note here is that there is no free lunch. Before I had this enormous sum or two sums. Now I have this. Okay, and the penalty that I'm paying here for having this is I have this indicator here, and I have this falling factorial. So this is not a kind of a simple function here. It's a kind of falling factorial, so I'm kind of stuck with this. Okay, so I traded this for this. But the exact for any set of parameters MF, F1, anything, they're exactly the same. Right? It's just that I understand random variables better than the sums. That's the only reason.
Can you remind what the condition I between 1 and F1 means?
This for F1 is the number of the slowest Qs. This is kind of this is the expression for potential bottlenecks. There is another expression for non-potential bottlenecks. Looks kind of similar but slightly different. The same flavor, right? The same flavor.
And F1 is something that's known.
F1, yes, that's a parameter of the model. You can look what are how many slowest Qs I have, right? You can look at the slowest Qs and how many of them I have. That's something that it's a parameter of the system. And this F1 can be 1. In that case, you have one Q that's the slowest, or F1 can be F. In that case, all of them are the same and all of them are the slowest by definition. Yeah. But high level, right? This enormous sum that I don't know what to do with, I replace with this. And and maybe now it looks, how is this any easier? Well, that's a question, right? Any question about the how what direction I took here?
The definition of a bottleneck is that the queue does not ever empty out.
No, that's not that. Yes, excellent question. That's why I say potential bottleneck. Potential bottleneck. So these are the slowest queues. They can be always busy, but there can be a regime where they're never busy. There is yes, that's why I'm careful to say potential bottleneck, but you get the idea correctly. Yes.
So why don't the potential bottlenecks, the LIs corresponding to those, enter the picture in your
Second, please.
the LIs, the geometric LIs? You only define it for
excellent.
Non-potential bottleneck.
Excellent question. So you note here that LIs only play a role through the sum, and so the non-potential, the potential bottlenecks, their parameter kappa 1 plays a role through this M somehow. That's where the parameter is hidden.
Okay.
Yeah, that was a good question.
So the falling factorial is coming from this like recursive type structure. Is that where
Something like that? Yes.
Okay, so it's hard to picture directly.
Yeah, I would say this is as messy as the sum kind, and that's kind of, there is no free lunch. If I wrote something very simple here, it would be suspicious how right? All right, so I'm going to work with this kind of representation. Again, I wrote this for potential bottlenecks. I have similar expressions for non-bottlenecks, non-potential bottlenecks, and the infinite server, something similar. Also involves falling factorials, indicator functions. All right, now, this is the representation, right? I'm looking for the regime where there are many customers. and I'm looking for the regime boundaries. Kind of, I want a landscape. Right? And the first thing I notice here, well, one thing that will determine what's happening here is this indicator, whether it's 0 or 1. Right? And that means it will be important whether the number of customers, how it relates to the expected value of m plus s. You know, if m is much larger than the expected value, this will be always 1. If m is much smaller than the expected value, this will be always 0. So this is one kind of boundary between the regimes. Somehow, this will be a critical number as far as the number of customers is concerned. And the second thing is, because of this following factorial, it will be important how f1 relates to the number of customers. Okay? And this, again, this is super vague right now. It's kind of just if you look at the expressions, right? So this is kind of the picture, right? Here I have f1, number of potential bottlenecks. With the orders of magnitude, I can have only constant all the way to the linear number, the number of customers, and then number of customers. Yeah, there is this m plus x expected value. That's kind of a line. It's a boundary, some kind of boundary. So by the end of the talk, I want to fill up this graph and say what's happening everywhere. Now, now a little bit about large deviations. I don't know how many people know about large deviations here. This is all super standard. So if I have some sequence around the variables, I can define a logarithmic moment generating function, right? And then based on that, I can define the rate function. And this rate function simply kind of characterizes probability that x is less than some x times m on the logarithmic scale. Okay, this is, so you can think of this that I'm doing something like this. I want to figure out xm less than like this. This is roughly some c in power minus m like this. This is this function. So this, I'm interested kind of what are the chances that I'm way below the mean? What are the chances I'm way below the mean? And this, that I'm way below the mean, probability that drops exponentially fast, and this function L characterizes how fast. Right? You know, this is well studied, you know, this L has nice properties, but in my case, the sequence of variables will be this m plus s. Now, here's, to make it a little bit concrete, here's my example. If m is Poisson with kappa 1 that grows with m, right? Then I can compute the logarithmic moment generating function. That's this. I can optimize to find the rate function. Turns out the rate function is this. Right? So the function looks something like this. So here is the mean. Okay. This is 0. And I'm dropping something like that. So you know, probability that I'm less than mean here is kind of 1, and that's why L is 0. But as I try to look probability from below some number that's less than mean, it's exponentially small. Right? This is L. This is, you can think of this. I'm looking really for this. This is large deviations. You know, typical large deviations. People look at the right tail. I'm here looking at the left tail. I'm looking at what is the chance that I'm much smaller than the mean, right? You know, if the mean is 1,000, you know, what the chances that I observe a value that's less than 100? This is what this says. Now, you know, why is that related? Well, here is my first regime. Okay? My first regime is what I call linear, and this says the number of potential bottlenecks is linear in the number of customers. Right? That's this. Okay? This. There is some F1 bar that's there. Okay? And then the representation, you know, I look at the ratio here to make this a little bit simpler. Okay? Now look what happens in this linear regime. Here's intuition. If m plus s, right, is some x times m, then probability that m plus s is around that number is this function here. This function here, right? I'm looking less than the mean. And now in large deviations, typically it would work like this. If I only had this indicator, right, you would say, what's the cheapest way to make this indicator 1? So you would say, I want to be right at the boundary. Right? I want to be right at m. That's the cheapest way to do it. Trying to push for something that's less is going to make it less likely, probability drop even further down. However, this is where it's non-standard. Because f1 is linear in m, this following factorial is exponential in m. So that, if I kind of make this m plus s smaller, this becomes bigger. So probability of this is dropping down, but probability of this is increasing. So the optimal value, the most likely value, or where the mass is concentrated in the expected value, is not at the boundary, but at some value psi, where psi you have to solve this optimization problem. Okay, so this is kind of making m plus s smaller makes this indicator always 0, but this thing is enormous and they compensate each other. And that's why here this expected value is roughly this, right? Where this psi solves this optimization problem. This psi solves kind of what's the most likely scenario that this happens. Okay. And then if this is true, then I look at these following factorials, right? Try to cancel that everything can be canceled. And if you think about these following factorials, there's something like this. There are these numbers that are multiplying, right? This is following factorial. Multiply. Think of this, all the numbers I have to multiply. That's the denominator. And the denominator, I have the same thing, but slightly shifted. So the shift is here by L. By L. This is kind of, this is this L here, right? And then we have these two factorials. You look at this and say, these things cancel. What's left is this thing and this thing here. Right? This is in the case where f1 is linear in M, and then what you get is you get this ratio in power L. This ratio in power L. So some kind of everything cancels, and all I'm left is with this. And then this is the first result. Like if I have linear regime, if I have number of filaments that's linear in the number of customers, this says all the Qs are geometric, but the parameter of the geometric distribution comes from solving a large deviation problem. You have to solve that psi that I talked about, and the most likely psi is this. Okay? For computational purposes, this is easier to use, but that's a kind of secondary point. So I'm estimating order 1 quantities. I'm estimating, is this filament consisting of 5 or 10 customers, but the parameter of the distribution has to do with large deviations. How unlikely is the behavior of m plus s? But because I have this ratio, right, I have 2 tiny quantities. I'm estimating them roughly, but because they're tiny, the kind of approximation error in them cancels, and I get something that's order 1. Okay. Now, this is kind of the first kind of regime, right? So I'm looking, this is the new novelty here. Large deviation somehow defines something that's order 1.
So from this, you can approximate the normalization constant.
From this, yes,
Accuracy.
I can also approximate the normalization constant. Yes, I didn't write it here. Yes, I can also approximate that. Absolutely, yes.
So this our eyes would be
the Qs,
Mhm.
the I type,
Yes, right.
and that's just the marginal.
It's just the marginal, yes. So if you're looking, let's say, if you're looking, I want to look at joint distribution. You can, the same will hold if you have 2 or 3 Qs, right? Only if you look at all of them together, then there'll be some dependency. But if you have a few Qs, that doesn't really change anything.
And you solve for your, here you have a phi that you don't know. Could you solve for that by using the
You mean
balance
this?
equations?
This one?
Yeah.
No, this is the solution of this equation. You see, that's why I say that the parameter of this geometric distribution
Yeah.
is defined by this equation that can be solved. But this equation involves large deviation rate of m plus s. Right? This L describes what happens with m plus s in an unlikely scenario somehow. But this thing here is order 1 quantity, right? This doesn't go to 0. This is order 1 quantity.
Yeah, could you solve it also by just using flow conservation in this limiting?
The answer is no, because yes, the answer is no. You couldn't do it. Because you see, the only thing that flow conservation would do it here, if I go back here, you would be back kind of to dealing with this sum. The flow conservation is already built in here. In a sense, when I said that these things cancel, all these things that I got from flow conservation, what is the rate in, rate out, kind of cancels out, and you're stuck with this. There is kind of no way around it. There's no way around it. So let me see here. Any question? Yeah.
So the scaling, can you
Uh-huh.
explain intuitively what's that? So little m, that's the number of customers.
Customers, right?
That's getting very large. We're also introducing a lot of very slow parallel.
Yeah. So I'm saying, what if I have number of slow queues that is linear in the number of customers? For I say number of customers is 1,000. I have slow queues that I don't know 50 or 100, for example. Right? This again, this is one regime. Let's say in this landscape. And the thing says, somehow the parameter of what's happening depends on this large deviation rate here. Which again, I don't know how I would extract that from that sum that I had at the very beginning. It's kind of like,
And the number of non-slow queues, that remains fixed.
fixed or not fixed, that's in that S. So that can be fixed or not fixed, doesn't matter. Everything is kind of covered here, all the case. That depends on kind of this S bar, which is the ratio of S and M, but it can be 0, it can be above 0, doesn't really matter. It can grow, cannot grow. Everything is covered here. Well, this is kind of, as long as the number of slow queues is large, the rest doesn't matter. Now, all right, so now just a couple of comments here. So the first one, the second one is here. What is the bottleneck here? And that's why I said potential bottleneck. The bottleneck here are the customers. He says, I don't have enough customers to clog the slowest queues. Right? There are too many slow queues to clog them. I don't have enough customers to do that. So the bottleneck in this model are the customers, not enough of them. If I had more customers, the throughput of the system would be larger. That's the limiting factor. Okay. And now this is just a special case. If all the queues are the same, right, then the distribution of the queues is geometric. But in order to find the parameter of this geometric distribution, we have to solve this quadratic equation. This quadratic equation somehow, this quadratic equation is kind of when you solve this large deviation thing, that's what stays out of it. Okay. Well, even in this homogeneous case, it's kind of not obvious, how this comes out. Okay.
When you say that the balance the customers, that means that the number of customers in the infinite server queue divided by m goes to 0, basically.
Ah,
Almost no one is in the infinite server.
no, no, no. The infinite server queue is not empty. The infinite server queue is not empty.
Okay.
When I say it's a bottleneck, how do I think about bottleneck? I say if I had more of that resource, I could increase the throughput.
Yeah, that's the truth. Yeah.
Right? So here, the throughput is fixed. How can I increase it? But the only way to do it now is to introduce more customers. This says the single server queues have more capacity to process customers, but there are not enough customers. And that's why I say the customers are the bottleneck. Right? Typically, people think about bottleneck as a queue. But because the system is closed, the customer can also be a bottleneck. It's like, I'm operating some kind of facility and I don't have enough customers. That's my bottleneck. All right, now here's another potential regime, right? So now I'm saying let the number of potential bottlenecks be sublinear. Okay, that goes to 0. And I have a few customers. So few customers means this. Few customers means this. Right? And again, I have the same representation. Now what changes? Now what changes? Now, because f1 is not linear in M, this following factorial here is no longer exponential in M. And this is almost always 0, and the cheapest way for it to be 0 is to be right at the boundary. Right? Before I was moving away from the boundary because this was getting larger and larger, but now this is not large enough. So the best way is kind of to be at the boundary, and then there is some algebra. The best thing should be in the boundary. All the following factorials cancel here, and what's left is 2 probabilities, and then some calculus, and turns out that this is the distribution. It's still exponential, but now the parameter is this derivative of the rate function at 0.1. Okay, so it's kind of like I'm looking always at this ratio, but depending on the parameters, things behave differently. Okay? So then the second result says, if I have sublinear number of potential bottlenecks and I have a few customers, then the number that I see in queues, the queue lengths, are also geometric, but now the parameter is this exponent here, again, that depends on the rate function of m plus s. Okay. And again, this can be solved numerically here to find out the number. It's not a problem. Now, in this case, still large deviations determine order 1 behavior. Now, customers are my bottleneck. Right? I don't have enough customers to increase the throughput. And then for homogeneous queues, things simplify. All the parameters of geometric queues are like that. So easy to compute for homogeneous queues. Now, the last regime here I have many customers. And then, again, back to my original representation, what happens here is that these indicators now are always 1. Right? Here, m is way bigger than the mean, so this is always 1. Right? So I can drop the indicator, it's always 1. What I'm left with is 2 following factorials, and then because f1 is less than m, the way this cancels is like this. So I obtain exponential distribution. Right? So depending on kind of like changing parameters, I kind of get different distributions here. Okay? And the point here is that in this regime, the bottlenecks are 2 bottlenecks now. The scale distribution of the number of customers is exponential. And roughly the order of magnitude of how many customers I have in a bottleneck is this. So you can think of this m minus this expected value is the number of excess customers. This is how many customers are stuck at bottlenecks. I have F1 bottleneck, so I divide by F1 to say on average how many at one bottleneck. But the distribution is geometric. Right? All other non-bottlenecks have distribution according to those special L's, what we predicted kind of from the very beginning. And the same thing for the infinite services.
In reality, the distributions are geometric, right? Like in the pre-limit sense.
Yes.
Yes. Okay. So something. Okay.
Yes. So that's why I say as m goes to infinity. Yeah.
So then scaled this way. Yeah. It's good.
Yeah. So as m is large. So maybe if I have time again, I'll talk about that as well. Yeah. So now I'm back into my picture, right? So this is kind of my picture. So my result number one was for this line, but actually it holds also here. It holds also here. This is result number one. Now, result number two covers this. Okay. And result number three covers this piece here. Number three. Okay. Now, I can take these two results, right? And I can check what happens if I kind of try to move this way or this way by setting parameters to be close to this line. And it turns out there is no gap there. So in other words, these two fully cover everything here. So you can obtain from here, you can go here and back. And also there is no gap here. Here, these results cover everything here. Okay? Now, what's not covered? What's not covered is this line here, right? And I don't know how to, if I try to go like this, I don't know how to do it. It's not obvious how these results would transform into this result if I set parameters to go that way. Okay. Now, what is this line? Okay, what is this line? This line is what's critical scaling. This says that this expected value of m plus s is roughly m, and that says that this indicator sometimes is 0, sometimes is 1, right? In all my regimes, it was either 0 or 1. But when you're exactly on that line, the probability that this is true is maybe some fixed number, 20%, 40%, 80%, something like that. And then things need to be much more delicate in estimating expectations. Okay. Now, there is one paper that kind of at the end I found out that deals with this case here. This one. And actually here, it's not even order of magnitude, it's actually 1. There's a paper that deals, there is one bottleneck, what happens? Okay. But from that paper, you cannot really extrapolate anything about this line. Okay. Because the paper uses something very, very specific about the case that have one potential boundary. Okay. So what's open is what happens on this line. How would that line glue these two together? Let's see. Any questions?
So a good question about how are the occupations of the queues in this regime? Are in all three regimes, for example, the infinite server queue, or are there m customers?
So here, yes. In short, yes. but it depends on what is this kappa 1 bar, right? This kappa 1 bar can also be 0. So
Yeah, that's not ordinary.
yeah, that's so the answer is it's this kappa 1 bar in this regime. Now, whether kappa 1 bar is 0 or not, it's up to parameters of your system. This result covers everything, whether this kappa 1 bar is 0 or not 0. So by choosing parameters, I can make it to be very small, or I can make it sizable. I mean,
So that's not a deterministic characteristic of any regime, whether that is.
Yes. So yeah, the true characteristic of the regimes is how many customers you have and how many potential bottlenecks you have. This is the true characteristic, I think, of all the regimes. Anything else it can be interpreted in multiple ways, I think.
But for example, in result one, it seems like you have order one in the queues, in the individual single server queues, order
Yes.
one customers.
Mhm.
And in the last one, you have order m customers, right?
So, say it again, please.
So in the result one, you get a geometric one. So that
Okay.
means that you have order one customers in the single server queues.
Okay.
And in the
Yes.
last one, it seems like you have order m customers, because when you divide L by something that's
Yes. So
you get like some.
that's right. Yes, right. But here also you have to keep in mind, right? I have here order one customers, but if I have order m queues, then the total number is also order m.
Yeah. But they're all empty and with positive probability.
That's
why
right.
they're
They're
not
all, yeah,
bottlenecks.
they're not bottlenecks. That's why I said potential
Yeah.
bottlenecks. Yes,
And the third regime, if they're each one, it's kind of full, then.
that's
those
right.
are the
It's a bottleneck. In that case, it's a true bottleneck. That's right. But here also I estimate how big is the bottleneck, right?
And in this critical line, you would have, in the single server queues, you wouldn't have neither order m nor order one customers. You'll have some other quantity.
That's yes. That's even orders of magnitude are not clear.
It will be like in heavy traffic.
It will be something like heavy traffic for a closed system, which I haven't seen yet anybody do. Yeah, that will be a critical kind of many server system in heavy traffic for closed system, which is kind of off the beaten path, I'd say.
Yeah, it's strange. Yeah.
Hmm.
Thanks.
Could we say that in that regime, again, the indicator will be 1 or 0 with positive probability.
That's right.
But whenever it's 1, it will be like the most likely scenario, like m plus s will be m, right? And then
Well, no, but very okay. So in that case, you have to. It's not enough. So here I work right kind of on the fluid scale. I said, how if I divide by m, am I off the mean or not? Here you have to kind of employ CLT or stable law in general to figure out how much you're deviating, right? Because here if you look at this indicator, right, if this is around the expected value, then you need to know what is the variance of this thing, how often it goes above m or below m. So you won't be able to do it without CLT or a stable law, I think, in general. Right, you can say that I solve the easy problems by saying indicator is 0 or 1, right? But even that required some large deviations. Now you have to be really delicate in how estimate this expected value. Well, yeah, that's a problem on its own. I mean, I haven't seen anybody even get to that point to discuss this regime. Any other questions? All right, so then I hope this is maybe the takeaway, right? I'm looking at all possible regimes, and this is 3 regimes plus I don't know what happens on this critical thing, which is a topic on its own. And then a few papers that are relevant, from the 70s to 2020s. All right. I hope I'm on time.
Yes.
Perfect.
That's Any other questions you have? Few minutes.
Quick question. So in the kind of analogous setting that you constructed with this typewriter font, LI and so on. Like, so you ignored the fact that these queues could be empty, right? Like these, you assume that the throughput was all kappa I, which meant like they were always full.
That's right.
So is there a way to like include that, like some probability of them being like the throughput is like some probability of being empty times kappa I, and then
Yeah, so I think what you're saying is, is there a way to adjust the probabilistic representation to fit this critical regime somehow? Yeah, possibly. I really don't know. I mean, obviously I try to do it a few special cases. I think some special cases are doable, but things get really steep very quickly. You have to be really careful how you estimate things. So I'm not too worried. Somebody tomorrow will say, "Oh, I solved it." It's okay.
Okay. In that case, let's proceed to the adjacent room for a short reception. And thank you again for the talk.
Okay.
it's like